So, the chapter we are going to start is the stability analysis. Basically, maybe in the previous chapters, we have seen that the output of any system tends to be either becoming it will either reach a final value which is finite, or it may tend to become infinite. For example, let me draw and show you something. All right, let's assume I have a system and going to give an input. Let's assume that the input is like a fixed value, like a unit step. Okay, this is the input. All right. At the same time, depending upon the system's parameters, like where are the poles, what is the gain, etc. We have many parameters, but let's not consider that for the time being. uh, Whenever you provide an input, it like this, it provides an output. Okay, let us assume that the expected value, if I say this is 1, I'm expecting an output of say 0.5. Possible, right? It can be even more, right? You can say that it can be expected output is 2. Let's say that is an amplifier. Okay, if it is an amplifier, I should amplify by whatever the gain is, right? For the time being, let's assume it is expected output is half. All right, it's not an amplifier, it's actually attenuator. You want to attenuate it by 50%. So zero point 0.5 is the expected output. So what happens is that you see it will not go to the zero point 0.5 immediately. It will, right? It will be like this. So you can see that it's going to reach the zero point 0.5 after some amount of time, right? There is a delay in other words, right? So this particular phase, right, during which your the output, right, will take some time to reach the actual desired output, right? So that duration is called as, this time is called as a transient period. There is a transition happening, right? Right. So that part is called as a transient. All right. Okay, so let me say, or I'll show you with the small transient now. So let me assume that, so it takes some time to reach the zero point 0.5. Okay, this is more clear. Now here, this the value is, right, zero point 0.5. The time taken till there, right? So this is what we call as the transient, right? So this is one case. Let me also show you another one, right? Wherein uh, multiple options we have, right? So there are systems which behave differently. So because of which I might have, right, even a completely different type of system. Okay, so it's maybe, right. Let's say this is the time, right? This is I'll just write magnitude. Same thing goes here. This is the time. This is magnitude. All right. Let me assume that once again I gave some input. I'll not draw the input now because I understood I'm going to get an output for a given input. So let's assume that the expected value of the output is this. So this is what I expected the output. But because of the system we design, right, we will not get this output, and possibly, right, let me assume. So we'll, I think you have seen a system like this earlier, maybe in your previous chapter. It is exponentially increasing function. Okay, it's a sinusoid and exponentially increasing. So if you remember, this kind of system is actually unstable. All right, so it actually starts from here, goes all the way till here. and so on. As the time in progresses, you know that its magnitude is increasing, and after some time the magnitude will reach to a value, right, which is outside the bound of our finite values, right? We say that it is going to be infinite, right? So now we have two cases, right, considered over here, right? That gives us an idea that whether the system will reach to the intended steady state. So the horizontal value is the steady state. Okay, I will mark steady state on both the cases. So here, this is the steady state. So here it actually reached the steady state. So other case here is this is the steady state. Before reaching the steady state, every system will pass through the transient period or transient state. Now you see in the second diagram or second graph, everything, the complete whatever you plot, even after this plot, whatever comes, that's completely a transient period. Correct? Right. So I'll write one statement now saying that uh, okay, every system passes through uh, okay, I'll directly bring up the word transient, passes through a transient period uh, before reaching the steady state. Right? Before it reaches the steady state, it has to pass through a transient state where the output is not equal to the expected value. Right? I desire that output is 2 volts, but it is not 2 volts. It's something else. Right? It will try. The system is trying to reach to that output during that phase. So there are two possibilities. After some time, your system might reach the steady state, right? Second case, output may not reach that state, right? So so in stability analysis, what we try to do, we try to analyze whether the system is going to, right, pass through the transient and reach the steady state or not. All right. So right, in uh, okay, let me write in a different way. In the stability analysis, we okay, in the stability analysis, we try to explore whether or not a given system passes through the passes through, sorry, not steady state, my mistake, passes through the transient state to reach the steady state successfully. So if this happens, we call that as a stable system, right? So that is stable system. Or not, right? In the sense, it will not pass through the transient state successfully to reach the steady state, right? So if it is not, we call this as the unstable system. So we try to identify whether the given system is stable or not ultimately. Okay. Now, for example, let's take an example. We are trying to measure, say, maybe measure the voltage at some point using a voltmeter. Fine. Okay. Right, on a circuit. Right. As soon as you put the probes into the positions and turn on the voltmeter, right? If it, assuming that this is the analog type of voltmeter, not the digital one, let's say. Okay, the older technique. As soon as you put the probes into the positions, what happens, right? The needle will start oscillating. Needle will not come to the final value of the voltage at the measuring points immediately. It will not come to that. There is small oscillations, right? It will oscillate, and then it shows a final value. So that oscillation state is the transient state. Okay. So once it passes that uh, oscillation state or the transient state, you will see that it will finally come to a steady state and right show a single value. Right. That is the example. All right. So you see that the system must pass through a transient period successfully to reach a steady state. So that's how the point of steady state comes into picture. All right, stability analysis is basically on this. Now, let us look at the various types of stability. All right. Right. Now, uh, let's consider a case like this. Okay, and okay, I need two of those. So copy. Okay, so now let's say that there is a container, right? There is a container, and initially I'm going to place a ball with some force. I'm going to put a ball inside this with certain amount of force. Okay, so that this is ball, and let's try to put a force, right? Let me show you a force like this. Right. So this is what I'm going to do now. So let us assume that the force is not very high, okay, with small amount of force, okay, right. So what happens is, right, this particular ball will go down, it will hit the floor, and it will definitely bounce back, but not since the force is not very high, right, the ball is going to remain inside the system, okay, inside this container, okay, within this container only. So I'll show you that something like maybe, okay, so I'll just try various positions of the ball inside this system. Maybe it will reach till here. Okay, same thing. It will come, even it may be coming back. Okay, like this the ball will move in this fashion, and then once again it will come back. Okay, so what do we understand here in this particular case, right? Basically, you apply the force, right? As the depth of the container is more, it keeps on oscillating and settle down at, right, some position, correct? Now you see, we assume that the force required to take out an object tends to infinity, in the sense always the object will oscillate when the force is applied, right, and settle down, and it will not come out. All right, so the point here to note is this. uh, as soon as this happens, what is going to happen, we'll write, okay, no need to write any explanation or something like that. We just want to bring one type of stability here, right? Always we will oscillate, and it will settle down, and it will not come out of the container. Okay, so such systems are said to be the absolutely stable system, right? So I'll just write, that means they are called as absolutely stable system. Okay, now let us try to consider a different system. Okay, so this is how it's going to you have right just like this, and let me assume that I will try to place the same ball at the tip of this place. Okay, so this is my intention now. Now what is going to happen? Right? As soon as I leave, right, the object is going to fall. Correct? It will never stay there. So the result I'll draw here in a different diagram. So it will either come this side or it will fall on the other side. Isn't it? Okay. So we try to keep we replace the container by some other object which is pointed object. All right, and we try to keep the that ball on the tip of that. Right. In this case, the ball will fall down without any external force. Correct? So that means it will always fail without, right? Even if you don't apply any force, right? It is going to fall down, indicating that this kind of system, right? Balancing is not possible. So this kind of system is called as the unstable system. Correct? Okay. So this is the second type of stability. Okay. Here the ball down without the application any external force, right? Such a system is referred to as unstable system. All right. Now, so what we do, we try to consider a different system now so that we can go ahead and identify some other type of system. Okay. So let us consider the, okay, so let's try to draw a different type of container now. So let's say the container is inverted cone. Like this. Mhm. Okay, now what we do? Uh, all right, we'll put the ball inside this again. So if I place a ball here and apply certain amount of force, I want to see what's going to happen. Okay, so let us say this ball all the way comes down till here. It will, right? I apply sufficiently large amount of force. Okay, it will come down and it will move to this position and it comes back. All right, so this is one possibility, right? There is another possibility which we had never discussed. That is, I apply I do the same thing, but I apply a huge amount of. So this will down and it will move up and it will go up. So there are these are the two possibilities. Okay. So let's mark. So I apply certain amount of force on this. Okay. This will move down. This will come back and it will come back. Right. This is one case we already have seen. Right. It's absolutely fine system, absolutely stable system. Right. The other one is this one. It will come down, up, and it will go out. Okay. Hope you are getting this. Okay. Okay. Right. Now, okay. Now we'll try to differentiate. Now I understand that in order to uh, decide whether the ball is going to come out of container or not, there is what is called as a critical value with which decides whether the ball will go out or it will remain within the container. Correct. So there is a critical value of the force. If you apply a value greater than that, it will go out. Okay. And if you put the force which is lesser than the critical value, right, it will stay inside. Now you see there is a condition. Correct. So there is a condition depending on which you will decide that whether system is stable or not. Okay, now you see, right? I'll write the condition here so that once we write, understand the next type over here. So here we apply the force F, which is lesser than F critical. Okay, but in this case, I apply a force which is greater than the F critical. Okay, right. Now you see, I'll write the statement related to the next case, right? Here, the stability depends upon certain conditions. You will decide whether the system is stable or not depending upon certain conditions. Correct? In this case, depends some condition on force, right? Force less than critical, force greater than critical, right? Some conditions are right. Depending upon the conditions, you may take up a decision that your system is stable or system is not stable. Correct? Such systems have they are categorized into a different right stability case, and it is called as the conditionally stable system. So if certain conditions are met, system becomes stable, otherwise unstable. Okay. Then the next case, in order to understand the next category, let's look at the case of what is called as a pendulum. So we know that the pendulum might oscillate, keeps on oscillating, right? Maybe like this. Okay, the extreme positions I try to mark, and maybe this is how it's going to Yeah, sure, sure, no problem. Okay, so the path of oscillation, let's assume that this is how it's going to be. Okay, now uh, the system keeps on oscillating when certain amount of force is applied. Okay, now is it stable? So I have a question. Is it stable? Because we define stability in certain fashion, right? And what is the definition of stability? You get your final constant value of the output, right? That's what is required. In the sense, it should be in the steady state. Whenever the system reaches a steady state, we call that, right, as a final value, and that is stable. Okay, now you see, I apply a force to a pendulum, it starts oscillating. So is this system stable? When it is in the oscillating state, when it is in the oscillating state, it is stable or not? No, see there was a definition for stability, correct? So let me go back. You see, in this case, take the first case, right? So it's the depth of the container is very large, right? Irrespective of whatever force you apply, the ball will never come out. So initially there is in a it is in a state oscillating state. It will keep on oscillating, right? Like I have marked in the second diagram. It will go out, go up, but it will not reach. It will come back once again, right? And it keeps on doing that, but finally it will come. It will settle down to a position that is the bottom of the container. When it settles down, you call that state as a stable final state. Okay, final state in the sense that it reaches what is called as a steady state. So when it reaches a steady state indicates that its position will not change. Okay, position should not change. It should be a fixed value. That's what we defined as a stable point. Okay, it's not going to make any oscillation. Doesn't matter whether it comes out or not. Okay, when it is oscillating inside the container, we called that state as a transient state. It is making the transition, right? And the final value, right, final position which it's going to hold, that will be the final state or the steady state. So the system reaches a steady state here, so that's why it is a absolutely stable system. Okay, second case, you simply see that as soon as I leave the ball at the tip of this object, it will fall. There is, you don't apply anything, it's unstable, right? Now the third case, force less than this, it will oscillate and comes to an end, right, comes to a fixed position, that is the stable, but depends on how much force you apply. That's why it is a conditional stable system. Right, now my question is that simple pendulum you consider and you oscillate, you apply certain amount of force. Okay, it starts oscillating, right? So according to our definition, when the pendulum stops, right, it is in the steady state or the stable state. Okay, but during the oscillation, it is not in the stable state, correct? No, no, no. It's not even unstable because it is making oscillations. That's all, right? Output is not infinite. Output is not something which is unknown to you. You know that it is going to make an oscillation. So this is something like, okay, I will show you the other option. Okay, I draw one system like that. So maybe I'll try to draw another response here, which I have not drawn so far. So okay, so let me do that. Gives you more clear picture about what we are talking about. Okay, so I'll slightly move this to the left, and let me try to draw another waveform. So maybe initially it will oscillate with the larger amplitude, but as the time progresses, you know that it will not make bigger oscillation. The right the span of the pendulum keeps on reducing. It's not like this always, right? After some time, it will reduce. Correct? This span keeps on reducing, isn't it? Right? The width of oscillation that keeps on reducing, isn't it? Right. So now let me try to write that here. So let me assume I want this to reach a steady state, reach the output to reach a steady state like this. But you see, initially it's not going to happen. So there was an unstable system defined in this way where the magnitude keeps on increasing. Now I will draw the opposite. Okay. Initially you are going to have a large value, but as the time progresses, it will become, it will be reduced to a smaller value. All right. Now say it starts from this point, it goes all the way to a maximum point, then comes down. This is how the oscillation takes place, right? So you see highest value, right? It reaches a maximum position, then comes down. But when it comes down again, the value is not equal to this. Okay, it's a smaller value. You see the oscillation keeps on reducing. And as the time progresses, right, you know that its value will come, right, closer and closer to the optimum value. And after some long time, it will come to the same point, which is the expected. Correct? So now you see, whenever it is oscillating, system is neither stable, right? It's not stable because it's not holding up a single position, correct? At the same time, system is not unstable, right? It's not giving you an infinite value. It's not giving you an unknown value, right? Under such case, we have a different type of system that is called as a critically stable. It's not unstable, so you can consider that as a stable. But yes, there is a chance if something goes wrong, it may be unstable, right? So that is called as a critically stable system, right? So let's try to give a definition of that here. The system is neither stable nor unstable, right? So we have a name given here, that is, it's a critically stable system. There is another name there, you may see the second name also in some of the textbooks. It's called as the marginally stable system. So we understood that what are the various terms present in our equation, in our right, in the general way of systems, we can classify the systems into these points as, right, we have various classifications. Okay, now let us look at the, let's look at the mathematics behind this. I simply said that output goes to infinity, output will become a finite value, etc. We simply called it by that. Okay, we simply call it. But now I want to understand that whether really it is going to happen, right? Whether the output is going to reach infinity really, right, or not, we'll verify. Okay, so that's what is coming up now, right? Right. So let's take an example to understand, right? Uh, what happens, whether the system is going to be unstable, and how does it look like? How the equation of such system looks like is what we are going to see now. Okay. So let's Okay, let's directly go to what is called as the uh, let me call it by the name. Okay, let's call it as a stability analysis itself. I'll call it as stability check, right? This is not what we are going to apply, right? When a question is asked to you, check whether the system is stable or not. But I'm going to do because as of now we have not never come across any method. So we will stick to the conventional method which you have studied in the previous chapters. Okay, we use whatever we have studied in the previous chapters to understand what do you mean by the stability. Okay, let us say there is a transfer function, right, of a system. So let us consider. So let's say that there is a system, transfer function is T of S, which is output, that is a C of S of the system divided by input denoted by R of S. Again, I'm using the standard notations. If you call it as Y by X, no problem. You simply call it as Y of S divided by X of S. Okay, so let us try to, let me write this. Okay, let's say the transfer function of a system is given by this now, this equation, 10 divided by S plus 2 to S plus 4. Okay, fine. Now let me assume that I give an input to the system that is equal to the unit step. Okay, let the input to the system be unit step function. When the unit step is given as input, right, I have to replace some value to R of S. What is the Laplace transform of unit step function? 1 by s. So unit step has a Laplace of 1 by s. Correct? So this implies this itself will be the R of S form. So therefore, let's calculate the output of the system. That is, now it is C of S. C of S is equal to given transfer function, that is T of S into R of S, isn't it? So let's try to write that. This implies the C of S is equal to transfer function. It's given 10 divided by S plus 2 into S plus 4. Multiply that with 1 by S. Okay, so in general, this is simply 10 divided by S into S plus 2 into S plus 4. It's clear? Okay. Now, so I want to find C of t because, right, all the graphs which we have plotted so far, they are time domain. So this is time versus magnitude, right? So that means, okay, I'll write a magnitude here, right? I need to come back to the time domain. So what you do, you will take the inverse Laplace, correct? So, but inverse Laplace is not straightforward here. Most probably you will apply what is called as the inverse Laplace can be taken in this case by doing the partial fractions. Okay, so anyway, I will not go to that level. Mathematics is not required as of now. Okay, so but let's try to do this. So let me call this is some constant a divided by s. This is how you split, correct? B divided by the second term s plus 2 plus c divided by s plus 4, right? Let us assume that yes, we know how to do this. We will calculate the ABC and we know the answer. Okay, so maybe a by 8 comes as 1 by 8, b is minus 1 by 4, c is 1 by 8. That's the answer here. I will not put that because we are not doing the calculation. Fine. Now when you have this, I can take the inverse Laplace. So inverse Laplace transform gives you C of t, time domain equation, right? Now a is a constant, a remains as it is, s becomes what? 1 by s, it is u of t, correct? Right, I can write it's simply u of t. Okay, next part, plus b into, what is the answer? If you recall the Laplace transform pairs, if you have 1 divided by, right, s plus s plus a, correct? Okay, if it is s plus a, its inverse Laplace will be e to the power minus at into u of t. So this is b into e to the power minus 2t u of t plus some constant c into e to the power minus 4t into u of t. Okay, is it fine? Okay, now, all right, what I do, I need some space in the middle because I need to explain you something more. What I do, I'll simply push this down. Okay, I'll bring it down. Okay, fine. Now, anyway, this is simply a rule that we are going to use. So uh, I'll mark this. So this is what I applied. Okay, fine. So, uh, okay, fine. So now I understand that this is the equation. This is the final equation which I am going to get. I can also try to write in order to understand this clearly. Right? What I do, I'll write it in the following format. This implies the final output C of t is equal to, this is a, u of t. I'll try to move it out and I'll write in a different fashion. Okay, some constant b into e to the power minus 2t plus a constant c into e to the power minus 4t. Instead of u of t, I'll write t greater than or equal to 0 because u of t is defined for every value t greater than 0, correct? So this is how I write. This is my equation. Okay, so if I ask you a question here, right, uh, whether the system is stable or not, correct? Whether the system is stable or not, I have to do one thing, right? System is stable if limit the t tends to infinity, in the sense you provide a huge large amount of time. Okay, you provide time, sufficiently large amount of time, and find the value of c of t at, as the t is a large number, right? Should be actually, this should be less than infinity, right? If this condition is satisfied, right, the any given system is stable. Right, now you apply this. This implies, right, limit as the t goes to infinity, c of t is equal to a is as it is, no problem, right? A is a constant plus b into e to the power minus 2 times infinity. Okay, that's 0 plus c into e to the power minus 4 times infinity. So you see that the last two terms, right, they will be zeros. So you have an answer equal to a, right? It's less than infinity. So you say that, yes, this is system is stable, right? Okay, now I'll give you a clear-cut definition of what some of the technical terms that we are going to use at a later stage. Okay, so uh, okay, now you see the system in terms of the given system is the t of s. Okay, the denominator of the c of s will have, right, some poles, correct? Because s plus 2 plus and s plus 4, if you try to plot on a graph, they are poles, correct? Whatever the roots of the numerator will be the zeros, right? And the roots of the denominator are called as the poles. This is what you already know, I guess, right? Right. Now, you see here, in this C of Sx equation, the poles which were present in the T of S, right? They are here, correct? They are here. B divided by something, right? And C divided by something. So those are what you call as the system poles. This is the term I wanted to introduce. Okay, one term. The second term, you see there is a by s. If you look carefully, the a by s or 1 by s is not in the t of s, correct? It came because of your input, right? So the pole which comes into picture because of your input, it has a different name. It is called as excitation, because excitation is your input, correct? Excitation pole, right? So there is one part that is coming because of the excitation, another part that comes because of the system. So system pole and excitation. Now let's come to the let's bring two more technical terms now, right? The result, the part of your result that comes because of the system pole, right, is the transient. It's a transient response. So previously we defined transient response is something that comes between when the system is in the transition period, right, starting from its original value of the output till it reaches a final destination, final value, correct, or a stable value. You check that initially you put t equal to 0, what happens? In the sense, put t equal to 0 to this, what happens? You have B and C present. But as the time progresses and t reaches infinity, these two terms will vanish. Correct? They are zero. You see, initially they were present, but later on they are not there. So it means it is a transient. Correct? Right? So that's why those that part of your response, right, which comes because of the system poles, right, is what is responsible for the transient response, right? So transient response comes because of the presence of the system pole. Then what you call this? What should be this? Can you guess? This is a steady state response that is coming into picture just because of your input. Depending on what input you give, this changes, correct? So that is the steady state. All right. So for any given system, you can expand, right, and write all the four terms corresponding to whether it is excitation pole, system pole, result is steady state or transient state or transient response. You can identify like this. So the things to remember now this whole system is stable, correct? So I'll directly give you an answer. So this is a it's a stable system. It's actually, according to our four classes, this is the first class. Absolutely stable system. Okay. Right. So using a conventional method, how to check that we understood now, but we have to do one more case here. That is, we'll start with another equation of T of S. We gave some input and we'll see that under what case this, right, becomes unstable. Will how, and later on we'll compare the both T of S. One T of S gave you five steady, one T of S like this, what we consider, this gives a steady state, right, is a stable system. We'll consider another one and we'll make sure that that's a unstable so that we can make a comparison, right? So that's going to happen in tomorrow's class.